And we'll go from current slide. And there's, I think I made this announcement last time, just want to check with you about the STEM jobs. Did y'all hear that? Okay. All three of you are transit students, aren't you? You're not Lawson students, so I won't do the other one. And I've announced it to all the classes, so if anyone wants to take this, you can have it. You go home, take it home with you, check it out, whatever. Feel free. Okay. Now, last time we were in Chapter 2 matrices, 2.4 elementary matrices, and we were doing this thing called the LU factorization. I think all three of you were here, right? And no, you weren't here. Okay. Did you pick it up on YouTube? If not, you'll probably need to. Yeah. But beginning on, like I said, Chapter 2, Section 2.4, page 80, bottom of that page, it says, once you have obtained the LU factorization of a matrix A, you can then solve the system of n linear equations in n variables. This, whoops, let me get my pen set up. AX equal B. We keep seeing this. That is the goal for a lot of linear algebra, is to solve equations like this, recognizing that that A may be an enormous matrix, and B could be a long, long vector, and the X could have many, 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 many components in it. But if you can take that big old A, break it into an L and a U, lower triangular, upper triangular matrix, then it becomes a lot easier to solve. Okay? So once you've obtained this, you can solve this system of n, where n can be a very large number, linear equations in n variables, very efficiently in 2 steps. Here are the steps. Okay? First, write. Okay? I know some of you have ebooks, but I can't tell if you all do. So write y, and this is a vector y, is equal to that upper triangular matrix U of x. I'm sorry, it should be just x. That came out pretty ugly. Let's see if I can clean that up just a little bit. Okay, Ux, the upper triangular matrix. Sorry. So write y is equal to the U, upper triangular matrix U, x, and then solve for Ly is equal to B. Okay? So what I sort of left off here, because I had already said it before, I didn't write it down. If take this matrix A, split it into A is equal to LU. L lower triangular matrix, U upper triangular matrix. With the U part, write the Y. You've just made up this new vector Y is U times X. Figure out what that is. Then do L times Y and set that equal to B. Okay? Well, wait a minute. What is the L here? Well, that's the lower triangular matrix. Okay? Solve L times that Y that you just did here is equal to B. Okay? 2. Solve Ux, which is equal to Y, remember. Okay? Equal Y, just what we had above, only reverse the signs on it, for X. And that's what you're looking for. Okay? Now, they sound like simple steps, but they look a little confusing, at least to me they do. Okay. The hard really all that hard, but is getting this A split into an LU matrix. The upper triangular is pretty easy. That's just doing your row reductions, just like we've always done. Not reduced row echelon form, but just in row echelon form, where you have, they don't have to be ones, but things on the diagonal and zeros below it. That's the upper triangular matrix, okay? While you're doing that, okay, you're keeping track of the elementary matrices that would have made that happen, and then doing the reverse, or the inverse of those in reverse order, and that gives you your lower triangular matrix, okay? So you've got the upper, and you've got the thing here. You come up with a U vector, which is the U times the X, okay? You have here. Now, that gives your Y. Solve this, that lower times that Y equal B. Figure out what the Y's are. So now you know what the Y's are. Take the U of X equal to Y, solve that, and you get what the X's are. Okay? Now that's all symbolically. Actually doing it is not quite so bad. Okay? It almost sounds like you're running around in circles again here. A lot of these do seem that way, but they really aren't. Column matrix X is a solution of the original system because this A, X, plus is equal to B. I can't write. Okay? That was your original issue here. That was what you're trying to solve. And we know that A is LU. X is equal to B. That's what it is. Just name this Y, okay, and LY is equal to B. That's your step here. And then plug back in that Y is your UX again. And set that equal to what you just calculated here, and you've got it, okay? And this is indeed equal to B, okay? The second step here, this is just back substitution because the matrix U is your upper triangular matrix. The first step is similar, except that it starts at the top of the matrix because L is the lower triangular matrix, okay? And so sometimes we call that forward substitution, and we were counting on you coming back. Okay, so here you are. Find you here. There you go. All right, middle part of the alphabet doing quite well. The first part and the last part a little on the weak side. All right, let's do example 7. Hopefully it'll make this whole thing make more sense, okay? But hopefully you've got down what we were just doing. Here's a linear system. X1 minus 3x2 is equal to negative 5. X2 plus 3x3 is equal to negative 1. 2x1 minus 10x2 plus 2x3 is equal to negative 20. All right. What's the first thing, your first approach? What would be your first step here to do? You're not quite ready for the steps they showed before. What do you do first?
Write the matrix.
Okay, write the matrix. X. Okay. I started writing the equations again. Don't do that. Okay, write the matrix. You tell me what the matrix is. 1, negative 3, 0. Stop there. Now, I know if we were solving this our old way, much shorter, Takes less time. You just do augmented matrix and go for it, you know. But we're doing it this method because that, even though it may be a little bit shorter at least one time through, if you had to do this repeated thing several times through for different values in the end, this LU method is going to be, LU method will save you effort later. So give me the second one. 0, 1, 3, and 2, negative 10, 2. All right. Now, what's your next step?
You want to turn that 2 into a 0.
That's it, exactly. You want that 2 to become a 0, because what you want is a 1 to be in the upper left. We got it. Bingo, done. Okay? Second, we want a 0 below it. Fantastic, it's already done for us. The third one, though, we want a 0 down there. Now, for those who weren't here before, this is just a little bit of reminder. If you step back a page or two, I'm trying to find it now. Okay, no. Just the previous page, the last thing we did last time. This is page 80, starting in the middle of the page. If A, which is what we've got here, that is A right there, row reduces to an upper triangular matrix U, that's what we're heading for right now, using only the row operations of adding a multiple of one row to another row below it, then A has an LU factorization. So in other words, if that upper left entry had been a 3, well, let's start with something easy, a 2. You don't want to change that to a 1, okay? But you're still okay because you can add row 3 to the opposite of row 1 and still get a 0, okay? If that were a 2 up there. If that were a 3 up there, you can still use it, but now you can be multiplying or adding to row 3 negative 2/3 of the top row. And then you get into fractions, and they really get messy. But you're still row reducing, but without the 1 there. With the 1 there, we're happy campers. We're really, really happy campers because you can only use multiplying one row by something and adding to another row. It's the only row operation, elementary row operation you can do to get this LU factorization. Okay, so you're absolutely right. We want a 0 there. How do we make that happen? How do we make that happen? Say this again a little louder. Okay, negative 2 times row 1 plus row 3. Perfect. Okay, now the new thing that we're doing now is also coming up with the elementary matrix, we'll call it E1, that does that same thing. And what would be the elementary matrix that did that same thing? 1, 0, 0, 0, 1, 0, help me. Huh? How about a negative 2? Negative 2, 0, 1. Remember, you're doing the same thing to the I matrix, the I3 matrix, as you're doing to this one. You're doing minus 2 times the top plus the bottom. So that would be minus 2 times 1 is minus 2, 0, 1. Okay. But we're really not interested in E1. We want to know the inverse of E1. So I think that's what Lauren may have been trying to tell me. What is the, I'm sorry, I said inverse of E1 and wrote E2. So I don't know where the brain is today. It's inverse of E1. What would that be? One, zero, zero, 0, 1, 0, 2, second, 2, 0, 1. All right. Now, if you have any doubt, then just simply multiply those two together. If you don't get the identity matrix, you've done something wrong. Okay? I think if you multiply these two in any order, it doesn't really matter. It should be the same. That would be 1, 0, 0. So that's a 1. That's what we want. 0, 0, 0. That's what we wanted there. 0, 0, 0. That's what we wanted there. 0, 0. I'm sorry. 0, 0, 0. That's what we wanted there. 0, 1, 0. That's what we wanted there. And a 0, 0. Did I do the third one? I'm getting myself on. Everything's fine so far. Now we're doing this in a second. So that would be a negative 2, 0, 2, which is a 0. Good. 0, 0, 0. That's a 0. And 0, 0, 1. That's what we want. Yeah, that is correct. That is the elementary matrix. The inverse of that elementary matrix. Okay. Why we wanted that, we'll see in a minute. Okay. What's the next? Oh, I didn't reduce this one. It's sort of important to do. There's 1, negative 3, 0, 0, 1, 3, and what did that give us? 0, negative 4, 2. Okay. Sorry, that's what we started out doing. I got off onto the other thing. It's negative. It's row 3 minus 2 row 1. Oh, goodness. My arm hurts. My shoulder hurts. 2 minus 2 is 0. Negative 10 plus 6 is negative 4. And 2 minus 0 is 2. So, yeah. Now, what's the next thing we want to happen here? Yeah, we want that to become a 0 also. And how do, okay, no. Okay, I understand what you said. You said divide that by 2. Normally, absolutely. But remember what I just pointed out? That one page. If A row reduces to an upper triangular matrix U, which is where we're heading here, using only the row operation of adding a multiple of one row to another row. So don't swap rows and don't multiply by a constant, non-zero constant. So what is it we want here?
We want to add 4 times 0.
Yes. We want that to become a 0. You get that by row, how did you say do it?
4 times row 2 plus 4.
Okay, 4 times row 2 to row 3. Okay, now let's go on and do it before I forget to do it this time. What will that produce? You leave the 1, negative 3, 0 alone, the 0, 1, 3 alone. What's your new third row? 0, 0, 14. Okay. Now, what elementary row operation, E2, did that same thing for you? This thing right here. Okay, 1, 0, 0. You didn't use the first row at all. And you used the second row but didn't change it any, so that's still a 1, 0, 1, 0. Okay? And what would be your new third row? 0, 4, 1. Now, what is the inverse of that operation? E2 inverse. I'm sorry, didn't allow enough room. Top row you don't change at all. Second row you don't change at all because you didn't. That doesn't change. What would be your third row? 0 what? -4, 1. That's exactly right, and you can go back and multiply those so you get that. So there is your E2 inverse. Okay. Well, stop the presses, halt the presses right now, because this is what? An upper triangular matrix. Your lower triangle is all zeros, so that's your U. That's your U. Okay, right there. Okay. Now, what we need to do is also get the L. Do you remember how we got the L? It's why we did the mess with elementary matrices to begin with. Remember what the L was? Product of the inverse matrices in which order? Yeah, 1 first, then 2 rather than. Okay. So that will be. I'm running out of room rapidly. Okay, so that's going to be E1 inverse is 1, 0, 0, 0, 1. That is a 0. It looks like a 4. 0, 1, 0, 2, 0, 1. And the second one is 1, 0, 0, 0, 1, 0, 0, -4, 1. Okay, when we multiply those two together, you're going to get a 3 by 3. Okay, first entry, what do you get? 1. Call it out to me. 0, 0. 0, 1, 0. Both of those are identity matrix looking. They produce that, exactly that. The only one that produces anything differently is the third one. What does that give you? 2. So that gives you a 2. Next. Okay. It's a 2, 2 entry that's 0, 0, -4. And 1. All right. And guess what that is, folks? A lower triangular matrix. That's your L. Okay? That's your L. Oh, yuck. It came out being a 4. I don't know why that happened. Except my pen hit it badly. So, what I'm going to do now, sorry about this, is erase a whole bunch of this stuff. Okay? We've already used it. I don't think we need it anymore, and for some reason, it's not erasing. Let me try it again. Here we go. Okay, I'm going to reduce that, erase that, and that, and that, and that. I don't need E1. I don't think I need E inverse either, do I? Okay. So let's get rid of this, and this, and that, and that, and that. Okay. I hope I don't need this anymore, or that, or that, or that, or that, or that. I do need L. I don't think I need these anymore. I hope not, anyway, because I just got rid of them. Okay, if I need it, I'll ask you and you can give them to me. All right, now we've got A split into LU. L down there, U up there. What do we do next? Here's the steps from the previous page. And maybe I should have written this too. Remember we had our A. What was the X vector? These are variables, by the way. X1, X2, X3. And then what other vector do we have? B is -5, -1, -20. Right? All right. Now with that in mind, what was the first step from the bottom of the previous page? Write a vector y, which I'm going to designate as y1, y2, y3, as what? Okay, it's ux. Well, here's your u, and there's your x, so that would be, I'll write it down. After a while, you won't have to do this, I think. The u is 1, -3, 0, 0, 1, 3, 0, 0, 14, times x. x1, x2, x3. Okay, and you tell me what that is. x1 minus 3, x2. Okay, what size is this, by the way? Yeah, this is going to be a 3 by 3, right? Yuck. Okay. What's the last? 0, right? Do you understand? Okay. What we're doing is a 3 by 1 by 1 by 3 is going to be a 3 by 3. Okay? 1x1 minus 3x2.
Oh, we multiply.
Yeah. Yeah, we're multiplying. And I hope I did this right. No, I didn't. Ooh. I got carried away. Okay. I'll probably need more room than I allowed myself. So let me squeeze. Okay. The first entry is x1 minus 3x2. Okay. Second entry is that's the 1. No, yeah, I'm sorry. It's a 3 by 1. 3 by 3 by 3 by 1 is a 3 by 1. Okay, sorry. I don't need any more room. Second entry is x2 plus 3x3. And the third entry is is 14x3. Okay. Now, that's your y vector. And what do we do with the y vector? Oh, I'm sorry, still on step 1. Then do an ly is equal to b. That's your lower triangular. And then you're going to do that times this thing, which is x1 minus 3x2, x2 plus 3x3, and this will be 14x3. Multiply L times this y vector. Okay? And what does it become? And again, you've got a 3 by 3 by a 3 by 1, so that gives you a 3 by 1. Okay? And the first two are pretty easy. x1 minus 3x2. x2 plus 3x3, right? The last one takes a little bit more effort. 2 times the top, that would be a 2x1 minus 6x2. Does everybody see what I'm doing? You're multiplying again. This will be just this one plus zeros, so that will be just this one. And 0 plus this one plus 0, that will be just this one. Okay. The third one, you've got more work to do. 2 times this minus 4 times that plus that. Okay? Now, I just got started. I said 2 times that. Okay? Minus 4 times the middle one. That'll be, I'm going to move my bracket because I know I'll need to. Okay? That'll be minus 4 times the second one. That's minus 4x2 and minus 12x3. Okay? That's the second entry here by second entry there. And then you got plus. I don't know where this is coming from. It just pops out of nowhere. Sorry. And finally, the third one here by the third one there, that's 14x3. Okay. There's your last row. Okay? And what do we do with that? We set that thing right here equal to B. And you know what we wound up with is exactly what we had to begin with. Okay? Which is kind of nuts. Why go through all this to wind up with exactly what we had before? So something's a little off here. Wait a minute. I left out something pretty important here. The LY, yeah, there is where it is. This thing we just got, set that equal to B. Okay? Okay. I thought that's what I was doing, but I must have gotten sort of lost in the sauce here. Okay. So that top entry there, and I don't have room to write it, this is equal to B. Yeah. I'm going to have to write it up here. Here is your B right there. Okay. Now that gave you and here's what they're doing that I'm not doing. I actually figured out what the y's were. They're leaving the y's in there. So basically we're doing this times that, and that gave you y1 is equal to -5. y2 is equal to -1. That's from the first two here. Setting this equal to that. The the product of this times that is equal to that. Y1 is equal to 5, Y2 is equal to negative 1. Y3 is, let's plug in what these other two are, okay? And if you see this, this is 2 times Y1, which will be negative 10, minus 4 times Y2, which is plus 4, and 1 times Y3, that's what we don't know, plus Y3, this is equal to negative 20. So that's just what they call forward substitution, okay? So this comes up to be minus 6 plus Y3 is equal to minus 20, and that gives you what? Add 6 to both sides, and that gives you Y3 is equal to negative 14. Okay, so now you have the three Y values. That's how what we plug back into UX. Okay? Okay, so here I'm going to erase this. Okay, this part right here. I'll erase that line too, it's in the way. Okay, now we know what these are. I'm using the same space because I don't have much room. So this was a minus 5, minus 1, and minus 14. This is such a pain in the neck. Okay. Now what we can do is go the other way, back substitution. Since you see here that the product of these are going to give you that, the product of those are going to give you that, and the product of this is going to give you this. We'll start at the bottom, okay? 14x3 is equal to 14. What does that make x3? Negative 1. And knowing that, then do this. 0 plus x2 plus 3 times minus 1 is minus 3 is equal to minus 1. Okay, x2 minus 3 is minus 1. Write that down. x2 minus 3 is equal to minus 1. Add 3 to both sides, and that gives you plus 2. So x2 is equal to 2. And now, back substitute, or whichever substitution is back again, on this one, x1, okay, oh, here I am, sorry. I've got it all over the board here. Yeah, this one, okay. x1 minus 3x2, where your x2 is, and this is what this is, okay? It's not the product of these. The product of these is that. What we're doing is finding out what this is. So I just don't have enough room to write it. So x1 minus 3x2, well, x2 was 2, so that's minus 6. x1 minus 6 is equal to minus 5. x1 minus 6 is equal to minus 5. So what would that be? Add 6 to both sides, and you get plus 1. 1, 2, negative 1. Okay. Oh, man. what a kind of a strange way to go about doing. Let me make sure I got it right. Yeah, 1, 2, negative 1. Sort of a bizarre way to go about doing this, but certainly it works. And I admit, it's far simpler just do a row reduction as the first thing. But this is because it's a simple system of equations. If this had been one of those that were even 12 or 13 equations with 12 or 13 unknowns, got to have that square matrix to begin with and get it into lower triangular. That's the first thing we do first, just by row reduction. Whatever that huge matrix is, get it, upper triangle first by row reduction. Keeping track of your e's, multiply those e inverses in reverse order. That gives you your L, lower triangular, okay? Then start by saying, you know that this times this is equal to your y's. And just write down y1, y2, y3. And then knowing that, and this is where I should have just put y1, y2, y3. This was all extraneous. I was trying to do literally what they said rather than, or figuratively what they said rather than literally. Okay? Okay. And just label this as y1, y2, y3, and use the lower triangular times that, and that should equal the b over there. And so you can figure out what your y1, y2, and y3 are. That one gives it to you, that one gives it to you. This one you just plug in those values and you get it. Okay? And once you know what that y1, y2, y3 is, that's what you plug back in here, and then start from the bottom and work your way up. And that gives you what your solution is. Okay? X1, X2, and X3. Okay. And calling them backward and forward substitution, I don't know. I get crossed up in what they mean by which, but it works. Okay? And that finishes 2-4, thank goodness, finally. Homework exercises here, any of the odds 1 through 7, either 9 or 11 or both, either 13 or 15 or both, 17, any of the odds 17 to 21. And by the way, the answers for these are in the back of the book. The odd numbers are in the back, and also the answers for the odds are at calcchat.com for worked out solutions to the odd number exercise. Not just the answer, how you get the answer. Okay, then do either 23 or 25 or both, 27 or any of the odds 27 to 33, and then there's a true-false 35, probably has that in the back of the book and also worked out, I don't know at CalcChat or not. 37, I'm pretty sure they don't have, I don't know, I'll let you figure that out if you want to do it or not. 39 they should be able to have in the back and at CalcChat. Then either 41 or 43 or both. Do 45. It should be in the back and at CalcChat. 47, I don't know if it's there, but you can read through that and think through it. Now, here again, they've done something that irritates me, but they do it. They come up with a brand new topic and definition and all that kind of stuff, and do it in the problems, not in the exercises, not in the text. Why would, if it's important, why wouldn't they put it in the text? But, and I don't even know how to pronounce this one. Does anyone know? Idempotent is the best I can come up with. Matrices, okay? I want to say idempotent, but I doubt if that's what it is, okay? Determine whether a matrix is idempotent. A square matrix A is idempotent if A squared is equal to A. Okay? So they ask you to identify whether they are or not 49 and or 51. And then
53 says identify A and B to make it idempotent, which is sort of going backwards. And then 55, 57, 59 are all proofs. You can do those if you'd like. You don't need to. Okay. Now, 2.5 is applications of matrix operations. And these get, I don't want to say super complicated, but they get complicated enough. They first start talking about matrices they call stochastic. And these are just some examples. Many types of applications involve a finite set of states, S1 through Sn, of a given population. So states, that doesn't mean Alabama, New Mexico, or something like that. States of a given population. For instance, the residents of a city may live downtown or in the suburb. They may vote Democrat, Republican, or Independent. They may buy Coke, Pepsi, or other brands, okay? The probability that a member of a population will change from the ith state to the jth state is represented by numbers. So basically this is what politicians use. I'll go on and confess this. I haven't lately, but plan to do more canvassing for certain political candidates in the upcoming November election. And what they do, they give us a list, the campaigns will give us a list of the houses to go to. What they've done, they've looked at the residents, they've looked at their voting history, they've looked at various things and say these are the most likely to be persuaded to vote for your candidate. Don't bother going to the others. Okay? How did they do that? With a matrix. And that's exactly what they're describing here. So this would be stochastic models. Okay? Now I can't say exactly how they did it, but that's exactly what's being described here. That would be voting. Consumer preference model. Whether you like satellite company A, B, or no satellite television. This would be a stochastic model. Okay? Consumer preference model. Whether you do probability you're going to subscribe, and do a variety of things here. That's another. Now, most of you have cell phones, right? Supposedly, I don't know if all of them do this or not. I think probably not, but you probably can get special packages that will encrypt your messages. They all are automatically encrypted, are they? I don't know this. I'm not big on cell phones. But you can get them so they are. For instance, I guarantee you in the military, because I was in the Navy, and we had one set of communications that encrypted everything. So you spoke into it, and the guy at the other end had to wait a while because it encrypted it when it left our end and got to his end, and then they unencrypted it before he could hear what we were saying. This was for classified or confidential or certainly secret or above operations you had going on. If you were telling a group of ships, we're going to fire on this thing, but we didn't want the enemy hearing this, you did that by encryption. Well, how you do encrypting things? Using a matrix, okay? They show you a pretty simple one here, and you can move it on up. On PBS, a few years ago, they had a series on some organization or something had an innocuous sounding name, but it was these gals who sat down and encrypted everything. Someone had broken the German code. I can't think what they call it. It was a really complicated code, and they were able to decipher all the messages, but it was tedious, really tedious. They did it this way. So encrypting messages, encoding messages, and decoding messages, all done through linear algebra. matrices. And then there's this other one, Leontief input-output models. And I find this every linear algebra book, I think, has this in it. And I find it so tedious going through it. But indeed, it is. And this guy sounds like he's Russian, right? But he's an American economist, Vasily W. Leontief, okay? Published a model concerning the input and output of an economic system, and he won the Nobel Prize for this work in economics, okay? So this isn't just little stuff. This is pretty major stuff. But this is how they figure, you know, how much to produce, what pricing to do. You can use all sorts of things using this input-output matrix. So then in statistics, they do a least squares regression analysis. If you're trying to figure out to predict what a result will be, you don't have exact data, but you have pretty good data, you can come up with a least squares model and predict to a reasonable effect what your outcomes will be. So that's done using matrices. So all these are examples of this. They're somewhat complicated, I want to say, in the application of it, but they're all doable based with things we've learned so far. I don't think we have time to go through those in great depth, but if you think you need something like this in your field of study, or one of these is more applicable than others, that coding, encoding, decoding, if you're in computer science, you might want to take a look at that. If you're in industrial engineering, you might want to look at those input-output models. You know, depending on where you are and what you're doing, in some of these, some majors, you might not see any application at all. Okay, fine, you can just skip them all. Okay, so we're going to skip 2.5. Now, I've given to those people who were here before, I think, the second test. Do all of you have that? You don't. Okay, let me get that one to you. I think that's it right there. I believe it is. Okay, here you go. Okay, and for those who were here before, I said you could do everything up until problem 10. Now you can do problem 10. In fact, I think you could have even done it just based on what we did before. Okay? So, anyway, there's test number 2. And I believe every one of you has turned in test 1. I still have one person who's not here who hasn't turned in test 1. As soon as I get that from him, I'll return those to you. Okay. Now, if the homework exercises at the end of each section haven't been enough, you could do any of the odd number problems in the review exercises. Any of the odds 1 through 5, 7 or 9. These are on page 98, 99 and following. 7 or 9, 11 or 13, 15 or 17. Any of the odds 19 to 25, 27, 29, 31, 33 or 35, 37 or 39, 41, 43, 45, 47 or 49, and then the others are those 2.5 sets. If you want to try to do some of those, welcome to try. Okay? Ready then to start chapter 3, determinants. Now this is the shortest and I think the simplest, because it's really focusing on one concept and one concept only of all the chapters we're going to do. I think we're going to finish this one pretty quickly, so that means we're going to have test 3 coming up really soon, so get working on test 2. So test 3 is dealing with determinants, and we've already introduced you to determinants, right? In a 2x2 matrix? Yeah, we talked about them. So let's see what else we can do with determinants. And this is just review because you've already done it. Okay? But we're going to do something a little different with it. Every square matrix, again, you have to be square matrix before you even think about determinants, can be associated with a real number called its determinant. Okay? And here's what, in generic terms, a 2x2 system of equations is. A11 x1 plus A12 x2 is equal to B1, right? A21 x1 plus A22 x2 is equal to B2. Now just plug in numbers for A's and the B's. Here you got a system of 2 equations, 2 unknowns, right? All right. If we were really solving that, I don't know if you remember by the oh goodness, what was it called? Something by addition method. Elimination by addition method. Okay? If we were doing that, one of the things we would do is multiply the top equation by, say, 8 minus A21 and the bottom equation by A11. I think I got the signs right. If not, we'll go back and change them. Right? And that way, these products would be the same but opposite signs when you add them together and you eliminate them. So it's elimination by addition. That's what we call it. Elimination by addition. But we got to do all of them. So let's do it. Okay? This would be A11 minus A11 A21 x1. Well, let me back up. Okay. Okay. Let me start this a little bit smarter, I think. Let's start with the bottom one. A11 A21 minus A21 A11 x1. Well, of course, that's 0. Okay. Well, okay. I think what I was starting to do before would make more sense. Okay. Just to keep it from being too confusing, which I'm making it more confusing, let's multiply that. That'd be minus A11 A21 x1 minus A12 x21 x2 equal a minus B1 A21. Okay? Down here we'd have A11 A21 x1 plus A11 A22. I just happened to notice I wrote an X for an A there. I hope I said it right, but I wrote it wrong. A21, okay. A22 x2 is equal to B2 A11. Okay. Now obviously you add these two together and you lose that term. So that gives you this. A11 A22 minus A12 A21 times x2 is equal to B2, let's do A11 B2 minus A21 B1. Which you could then say x2 is equal to A11 B2 minus A21 B1 divided by this thing, A11 A22 minus A12 A21. All right? Now, if you had multiplied the top equation by minus A22 and the bottom equation by a positive A12 and done the same thing, you would have eliminated x2 and come up with x1. Okay? And without doing all that, because it would take me another board full, let me just write down what the result would have been. X1 is equal to just to get my signs right. And they actually wrote the B's first. I thought they would do it the other way. B2 A11, no, 22. Let me start over. Okay, X1 is equal to B1 A22 minus B2 A12 divided by A11 A22 minus A12 A21. Okay. Now they wrote them in different order, but it's still the same thing. Okay? Now, looking at these two results that we have there, and I really should have done X1 first and X2 to keep it in the same order as the book, but I just did what came first. What do you notice about those two solutions for X1 and X2? First thing that pops into your brain. Don't worry about the order I did things. Look at the things that are common to those two. Anything?
The denominator.
The denominators are identical. They really are. They're the same denominators. Okay? So, let me hit something else here. What can that denominator never be? 0. Okay? So there's the first thing to do. For this to have a solution, that denominator cannot be 0. Either one of them, because they're the same, right? Now let's see what that denominator is. A11 times A21 minus A12 times A21. Does that ring a bell? A11 times A22 minus A12 times A21. That's your determinant. And remember before, we said for this to have a solution, the determinant cannot equal, for it to have an inverse, the determinant cannot be 0. So for the system to have a solution, the determinant cannot be 0. So there's something we've already run into before. The determinant of your coefficients can't be 0. Now, let's look at this X1. There's some things that look pretty similar. The A22s are the same here, and the A12s are the same here. Okay? It's just that B1 and B2 have replaced A11 here. B1 has replaced that, and B2 has replaced A21. Oh, guess what? Those are the coefficients of X1. So to get the solution, we look at the determinant of, we just substitute B1 and B2 in for the coefficients here, do that determinant, right? B1 A22 minus B2 A21. Yeah, B2 A12, sorry about that. And you get your coefficient, your numerator. The denominator is the determinants of that. Your numerator is the determinant when you substitute the constants in for your coefficients there. And then look at the x2. The x2 denominator is the same. We already determined that. But now we substitute B1 and B2 for these coefficients. Do its thing. That would be B2 A11. B2 A11 minus B1 A21. And there it is. Okay, determinants are all over finding those solutions. Is that the easy way to do it? No, not particularly. But it certainly shows you some uses for determinants. Okay? So, let's do our definition here that we've already hit before, especially for a 2x2. We haven't said how to get it for anything bigger. So let's start it with a 2x2. The determinant of a matrix. Now I'm going to start giving a couple of definitions here, or shorthands. Rather than writing determinant, you can write DET of matrix A. Okay? And here's A, here's matrix A. And you know this already. It's A11, A12, A21, A22. Okay? And you tell me what the determinant of that is. A11 times A22 minus, second, A12, A21. And it doesn't matter which order you write those. Just make sure your minus sign is with the correct one. Now, let me give you my preferred, even shorter abbreviation for determinant. It's this. That means determinant of A. Now, that almost looks like absolute value bars. Don't confuse them with absolute value bars. But with absolute value, you just get one number, right? With a determinant, you get one number. Absolute values always have to be positive. These do not always have to be positive, okay? So don't confuse that. But that's the shorthand for determinant, okay? And that's exactly what it is. Determinant of A is that. And for a 2x2, it's just simply the cross. This cross, the product of the main diagonal minus the product of the other diagonal, the non-main diagonal. Okay, that's only for a 2x2. So let's do example 1. These shouldn't take very long. Here's A, 2, -3, 1, 2. You tell me what determinant of A is. Seven. Perfect. Everybody see that? Product of the diagonal is 4, minus the product of the anti-diagonal, the other diagonal, minus the minus 3 is 4 plus 3 is 7. Very good. Okay? Here's matrix B. 2, 1, 4, 2. What's the determinant of B? 0. Very good. Here's matrix C. 0, 3 has 2, 4. What's the determinant of C? Second? 3. Or -3, isn't it? Causes. Yeah, product of that is 0 minus 3. Okay. Excellent. Excellent. Now, when you have bigger matrices than 2 by 2, 2 by 2s are a piece of cake. I love them. They're so simple. But when you have a bigger one than that, to define a determinant of a matrix of order higher than 2, it is convenient to use, they say it's convenient to use, minors and cofactors. And frankly, to me, the names are the things that get me. You use them without really worrying about them, but the names and keeping up with what's called what, that to me is a pain in the neck. Okay? You use them all the time, but naming them. So let's go through so you'll see what their names are, and hopefully you won't find it too confusing. So, we start with A being a square matrix, meaning an n by n matrix. Okay? Then the minor and that's called capital M, and it's given a suffix ij. Okay? Of the entry A sub ij is the determinant. Okay, I'm going to abbreviate that. Of the matrix obtained by deleting the ith row and the jth column from A. Okay. That's the minor. The cofactor, okay, Cij, okay, of the entry Aij. So these are all referencing some entry that you happen to pick out, is Cij is equal to -1, now this is way too confusing a formula, raised to the I plus j power times Mij. So, the Mij, the minor, is a determinant, okay? A number represented by deleting the ith row and jth column from A, taking the determinant of the matrix left over. Then Cij, the cofactor, is exactly that number, but with a plus or a minus sign on it. Sometimes it's the same sign, sometimes it's not the same sign. Okay? I know that sounds really bizarre, but it's so much easier to do than it is to describe. Okay? So we will do it. Okay? Now we'll start doing it what I call the complicated way. This is generic, no numbers to speak of except subscripts. A11, A12, A13. This is a 3 by 3 matrix. A21, A22, A23. A31, A32, A33. Okay. Now, notice where both of these started is you pick an entry, Aij. I don't care which one you pick. Pick any one of those. Let me clean up this last one because it really looks ugly. Okay, that looks a lot better. Pick any one of them. I don't care. Pick one. Anybody. Any one of those 9 entries.
A13.
A13? Okay. Here's the one she picked, A13. Now, what you do to find its minor is to wipe out the first column, wipe out the third row. There is your minor. Well, no, that's not quite. That's the matrix from which you get the minor, and the minor will be the determinant of that. That would be A21, A32 minus A22, A31. That is the minor 1, 3. Okay? That's the minor. It's just that determinant. When you wipe out the row and column for which that entry was chosen, what's left over gives the determinant of that gives you the minor. Now, what the cofactor is either plus or minus that number. And here is the easy way to tell. Rather than doing 1 plus 3 is 4, and we raise minus 1 to the 4th power, you get plus 1. So that means you keep this positive, whatever this number is. Okay? Here's the easier way. Start here with a plus. Always with a plus. Plus minus plus. That's a plus. Plus minus plus minus plus. Plus minus plus plus minus plus. Plus minus plus minus plus. Plus minus plus minus plus minus plus. It's always going to come out that way. If you just go right, left, up, down, don't go diagonal. But if you do the other, it's always. So it's going to be plus, minus, plus, minus, plus, minus, plus, minus, plus. So just looking at it. And see, if these two add to be an even number, it's pluses. Okay? If they add to be odd numbers, they're minuses. Okay? So every other one's a plus and every other's a minus. So the cofactor of this, Cij, would be exactly the same as the minor. It would be that. This is also C1, 3. Okay. If you had chosen one of the others that was a minus, I'll let one of you choose that. You choose another entry, but this time, well, I'll tell you whether it's one I want to deal with or not. Choose another entry, not 1, 3.
A22.
Second?
A22.
Okay, I don't want to do that. Second? 3, 2. Okay, we're going to do this one, right? Wipe out that column and that row, and the minor M32 is going to be what? The determinant of A 1 times A23 minus A13 A21. Okay? What would be the cofactor of 3, 2? The opposite of that, because plus, minus, plus, minus. It's going to be the minus of that. Minus the minor of 3, 2. That's all it is. The cofactor is the same number as the minor, sometimes with the same sign, sometimes with the opposite sign. Okay? It's just depends, because these two added to be an odd number, that makes it negative. Because these two added to be an even number, that makes it the positive. Same sign. Okay?
Does this only work for like a 3x3 matrix, or can you go like?
You can go as big as you want to, but of course then your minors are going to be of a, if you went to, give me a matrix size.
5 by 5.
5 by 5, okay? So when you did the minor, if you had 5 columns, 5 rows, okay? You pick something inside there, wipe out, say that, and then you're left with a 4 by 4, right? And then you wipe out, yeah. So every time you do you just lose one dimension in each way, and then to get the determinant this, then you have to do a determinant of a 4 by 4, which then you do the same thing again. Then you do a determinant of a 3 by 3, and And then when you get the 2 by 2s, you just do this. Okay. So yeah, it's the same thing, but they just get bigger and bigger and bigger. But they follow a very definite pattern, which, and we'll see how to do it. Okay. But yeah, you do the same thing for the bigger ones too. We're going to stick with 3 by 3s for just a little while, just to get used to it. So let's do example 2. Yeah. Whew. Find all the minors and all the cofactors of this matrix A. 0, 2, 1, 3 minus 1, 2, 4, 0, 1. Okay. Let's do it very regularly. So let's do first the minor 1, 1, minor 1, 2, minor 1, 3, minor 2, 1, minor 2, 2, and minor 2, 3, and minor 3, 1, minor 3, 2, and minor 3, 3. Okay? I hope I left enough room. Okay. Minor 1, 1, what would we do? Wipe out the first column and first row. You're absolutely right. And what we got to leave the minor to be? Negative 1. Is that what you said? Yeah. Okay. All right. Done. Which one you want to go to next? 1, 2? Yeah or nay? You can go anywhere you want to. Just tell me.
Yes.
1, 2. Okay. Then let me wipe out that one. And what will be our first step then? Already wiped out the first row. Second column. Okay, now do your minor. Negative 5. Perfect. Want to do 1, 3 next? Okay. That would mean wipe out the third column. And what does that give you? Positive 4. Okay, because it's 0 minus a minus 4, which is positive 4. Okay. 2, 1 next. Or let's just do 2, 3 next. Is that okay? That means I have to erase less. Okay. We'll do 2, 3. 2, 3. Okay. Negative 8. Okay. Let's do 2, 2. I'm just being really lazy about it. Negative 4. And let's do 2, 1. Nope. 2. Buckle my shoe. Okay, now. See? Because it's minus a 0. Okay, 2 minus 0. It's just 2. Okay? Let's do 3, 1. Five. 3, 2. Negative 3, and 3, 3. Second? Negative what? Okay, negative 6. Perfect. Now let's do the cofactors. C11, C12, C13, C21, C22, and C23, C31, C32, and C33.
Did you say if it's even, it's positive?
Okay, there's the rub. Depends on what the it is. Okay, if the sum of that is even, you don't change the sign. If the sum is odd, you do change the sign. It's the negative of what you got there. If it's even, it's what you got there. Okay, it's not necessarily positive. It's what you got. So what's C11? Negative 1. C12?
5.
C13? 4. C21? Negative 2. C22? Negative 4. C23? 8. C31? 5. C32? 3. And C33? Negative 6. Perfect. Way to go. Any questions on that?
Can you say that rule one more time?
Okay. The rule is add the subscripts together. If they're even, it's the same number as you had there, the positive of that number. If they're odd, it's the opposite of the number. Negative 1 times the number. So that made that change. Okay. Now, in real life, I never mess around with these. Calculating the minors are pretty easy. Well, usually I start with the sign. Okay. So pick that one. I say that's a positive, and then I just do whatever that is the positive of that. If it was this one, that's the negative, and whatever that gives me, I change the sign. And I don't go through figuring out what is the minor and then what's the cofactor, and doing all this thing. I sort of do it at once. And I think once you get going, you'll find out you do it at once too. But that's technically what you go through to do it. I never think -1 to the I plus j power. I just don't even bother with that. It's the positive of this number or it's the negative of that number. That's all. And I just count over and see if we can do it. So I think we got them all right. Let's just check and make sure I didn't do a dumb mistake somewhere. It looks like all of them are correct. Yeah. Okay. Now, here is a definition. I guess some of you don't have books, so let me write this down. The determinant, sorry, my voice is going on me, sorry. The definition of the determinant of a square matrix. This, again, is a really wordy definition. I think you'll find it's easier to do in reality than it is to read through this definition. Okay, in order to have a determinant, the matrix must be square. Okay, got to be square, n by n matrix. Okay, of order n greater than or equal to 2. Of course, a 1 by 1 matrix, whatever the number is, don't even mess with that. It could be equal to 2 or greater than 2. Okay, then, if that's the case, you got a square matrix order 2 or more. The determinant of A is the sum, okay, of the entries Oh, here's where I really don't like this. We're going to say it this way and then change it later. Sorry about this. the entries in its first row multiplied by their respective cofactors. Okay? That is, the determinant of A is equal to, if you're using the first row, that would be the summation from J equal 1 to N, if this is an N by N matrix, which we said before, is A 1J, that's the first rows, and the jth column is going from 1 to N, times C 1J. Okay? Which is, by the way, A11, C11, plus A12, C12, plus A13, I said A and wrote C, 13, C13, plus dot, 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 all the way up to A1N, C1N. Okay. Now, remember, every one of those C's may have 1, 2, 3, or more determinants in them. Okay, so it's got, you're doing determinants with determinants with determinants. Okay? Now, of course, go back to a 2 by 2. So I is 2, and that would be A11 times this cofactor would just be A22, right? You wipe out the first row, first column, okay, minus A21, A12, this cofactor would be minus the column of the location, and that would be, stop there. Now, when you use this definition, you are expanding by cofactors in the first row. Okay? Now, I kind of wish they'd gone on and given you the general to begin with. Okay? Later we're going to say, it doesn't have to be the first row. It could be any row. And then they're going to say, yeah, it doesn't have to be any row. It could be any column. So pick whatever works best. And I think you'll find what works best is the row or the column with the most zeros in it. That's going to work best, okay? And we'll go from there. But let's just do the 3 by 3 in example 3 using their definition. And this will work perfectly fine. Here is A, 0, 2, 1. It sort of looks familiar, doesn't it? 3, negative 1, 2, and 4, 0, 1. Now, frankly, if generically you just told me to find the determinant of A, I think I would have chosen the first row, okay? Because it has a 0 in it, and the other coefficients are small. The column 2 would have worked almost as well, it's just that one of those happens to be a negative, okay? Any of them would work. Row 3 would work quite nicely, and column 1 would have worked okay, Any of them would have worked, but those would have been the easiest. Row 2 and column 3 would have been the most work to them. So avoid them if you can, okay? But it doesn't matter which one you do. Let's use row 1, okay? Now, what do we say it was? You pick the first entry here, 0, and multiply that by the cofactor, right? which is, because this is in the 1, 1 position, in other words, the plus position, that's going to be times a positive of anybody?
Negative 1.
-1, okay? The positive value of -1, which is -1, not, yeah. It's a plus position, so you don't change the sign of it, okay? Now, if you're going on down, the next will be, and here is frankly, let me back up a moment here, okay? Let me tell you what I actually do most of the time, okay? I start with the position. That's a positive position, so I put the plus here, 0 times, and then I just do the determinant. So I put the sign, rather than doing minor and cofactor, I put the sign up front and then just do the minor, determinant of the minor. That's the easier way to go, okay? So that would have been a -1, giving you still 0. I mean, nothing has changed here, okay? Now, this is how I do it, okay? Okay, go to the next one. The entry here is 2, but it's in a negative position. So I put -2 and then do the determinant that's left. And what's that? -5. So it's easier to get the sign out front. Don't mess with cofactors. Deal with the sign, okay? And then what would be the next one? What's that?
What do you mean when you say 2 is in a negative position?
Okay, one more time.
What do you mean when you say 2 is in a negative position?
Okay. Again, I don't mess around with the I plus J. I look at this and say plus, minus, plus, minus, plus, minus, plus, minus.
Oh, okay.
Yeah. This is in the plus position. That's in the minus position. That's in the plus position. The next one I'm going to do is +1. Doesn't matter. It's in a plus. Oh, let me get my pen back. +1 because it's in a positive position, and then do this. What does that give you? 0 minus a -4. Remember, you're the determinant. 0 minus a -4. Remember, it's positive the downstroke, negative the upstroke. Remember, if this is the thing you're doing the determinant of, what would you do? 3 times 0 minus 4 times -1, right? So minus 4 is +4, right? Okay. Bless you. Okay, that gave you 0. That gave you 10 plus 4 equals 14. There's the determinant of A. Right? Okay. Now, I guess we'll stop there. Okay. I won't give another counterexample. And that's what they got to. Now they say, after they do that, although the determinant is defined by the expansion of the cofactors in the first row, it can be shown that the determinant can be evaluated by expanding any row or column. Okay? So, since we don't have much time, let's just do that quickly. Okay? All right. I want you to choose a different row or a different column. I really don't care. Well, I do a little bit. Okay. I said I thought the first row was the easiest. The second column would be just about as easy. Right? So let's try that one. Let's do the second column. Okay. I'm going to put an arrow there. We're going to go down. Okay. Now I start with the first letter there. What's the sign of that position? Negative. So it'd be a -2 times So wipe out this, and what do you have left? Okay. Negative 5? Yeah, negative 5. Okay. Now, okay, I'm going to continue down that column, right? What's the sign of this position, the negative 1 position? The sign of it. Plus, minus. Huh? Okay. I'm not saying the sign of negative 1, the sign of that position.
Oh, positive.
Okay, that's a positive. That's going to be plus a negative 1. You don't have to write them this way, but this is what I'm trying to emphasize here. This time we're going to wipe out that one, and what will be left? Negative 4. Okay, and then let's get to the third one, and this is really going to be being obnoxiously anal retentive here. Wipe out that, and what's the sign of that position? Negative. But the number there is a 0, right? So who cares? And what's your determinant? A negative 3. Okay, what do we have here? Negative 2 times negative 5 is 10. And minus 1 times minus 4 is 4. Minus 0, okay, or plus 0. I don't care which one you put, it's 0, okay? What does that give you? 14, same as we got before. You can do any one of them. Pick a row, pick a column, and go along that one, and you can get the determinant of that matrix. Now, how are we doing on time?
We have 1 minute left.
Huh?
1 minute.
That's what I was thinking. Okay. So I was going to show you another way to do a 3x3. They're going to show it to you in a page, so I won't do that now. Okay. So we're going to start at the top of page 107, another theorem, basically doing almost the same thing we're doing now, but we'll go from there. So there's where we'll begin next time. Let me give you homework exercises out of these. I think you can do any of the odds 1 through 11. 11 sort of interesting. And I think you can do any of the odds, either 13 or 15. Okay, I think you can do 17 for sure. I think you can do any of the odds 19, 23 is a little more, okay, 19 through 25. We'll hold off doing the bigger ones later. Of those, I think you'll find 21 is the easiest, and probably 23 is the hardest, okay? But give them a shot. We'll pick up the rest of those next time. Any questions? All right, good deal. And it seems like we were just had one, but it wasn't a real one. I was going to say, have a good weekend. Felt like we almost had a weekend. It was just a real short weekend, a holiday. Okay, so we'll